Group 2 of the periodic table is known as the alkaline earth metals. These elements form the second vertical column of the periodic table and belong to the s block because their last electron always enters the s orbital. The group 2 elements are beryllium, magnesium, calcium, strontium, barium, and radium. Unlike group 1, hydrogen is not included in this group. Although these elements have many similar chemical properties because of their similar electronic configurations, each element becomes larger and more reactive as we move downward through the group. The most important feature of every group 2 element is that it has 2 electrons in its outermost shell, which are called valence electrons. Because of this, every group 2 element has the general outer electronic configuration Ns. In this notation, the letter N represents the principal energy level or shell number, while S means that the outermost s orbital contains exactly 2 electrons. Since the s orbital can hold a maximum of only 2 electrons, the outermost s orbital of every group 2 element is completely filled. These 2 valence electrons determine the position of these elements in the periodic table and control almost all of their chemical and physical properties. The image shows the electronic configuration of each group 2 element. Beryllium has the electronic configuration 2s, which means that after the helium core, there are 2 electrons in the 2s orbital. Magnesium has the configuration 3s, calcium has 4s, strontium has 5s, barium has 6s, and radium has 7s. Although the principal energy level changes from the second shell to the 7th shell as we move downward, every element still ends with S. This common outer electronic configuration is the reason why all group 2 elements have similar chemical behavior. The atomic models shown on the right side of the image help explain another important trend. As we move downward from beryllium to radium, the number of electron shells increases. Beryllium has 2 electron shells, magnesium has 3, calcium has 4, strontium has 5, barium has 6, and radium has 7. Although the number of shells increases, every atom still has exactly 2 electrons in its outermost shell. This is why all of these elements remain together in group 2 of the periodic table. The 2 valence electrons play the most important role in the chemistry of group 2 elements. Like all atoms, these elements try to achieve a stable electronic configuration similar to the nearest noble gas. They can achieve this stability by losing both of their outermost electrons. Once these 2 electrons are removed, the next inner shell becomes the outermost shell, which already has a complete and stable electron arrangement. Therefore, group 2 elements usually lose 2 electrons during chemical reactions, when group 2 elements lose their 2 valence electrons. They form positive ions carrying a +2 charge. These ions are called divalent cations because they have a charge of +2. For example, beryllium loses 2 electrons to become B, magnesium forms Mg, calcium forms Ca, strontium forms senior, barium forms Ba, and radium forms Ra. Every group 2 element forms an ion with the same +2 charge because every atom loses exactly 2 valence electrons. The flow diagram in the image summarizes this behavior very clearly. It shows the sequence group 2 NS configuration 2 valence electrons forms M-ion moderate reactivity. Here, M simply represents any metal belonging to group 2. This flow explains that having 2 valence electrons causes these elements to lose 2 electrons during chemical reactions, producing stable M-ions. An important comparison shown in the image is between group 1 and group 2 ions. Group 1 elements have only 1 valence electron, so they lose 1 electron and form M-ions. Group 2 elements have 2 valence electrons, so they lose 2 electrons and form M-ions. Because removing 2 electrons requires more energy than removing 1 electron, group 2 elements are generally less reactive than group 1 elements. However, they are still considered reactive metals because they lose electrons relatively easily compared with many other elements. As we move down group 2, the size of the atoms gradually increases. Each new element contains one additional electron shell compared to the element above it. The extra shell increases the distance between the nucleus and the outermost electrons. At the same time, the inner electrons shield the outermost electrons from the attractive force of the nucleus. This phenomenon is known as the shielding effect. Due to this shielding, the nucleus cannot hold the outermost electrons as strongly. Because the outermost electrons are farther from the nucleus and experience greater shielding, they become easier to remove. As a result, reactivity increases down group 2. Beryllium is the least reactive member of the group. Magnesium is more reactive than beryllium. Calcium is more reactive than magnesium. Strontium is more reactive than calcium. Barium is even more reactive, and radium is expected to be the most reactive member because it has the largest atomic size and the weakest attraction between the nucleus and its outermost electrons. The increase in atomic size also affects another important property called ionization energy, which is the energy required to remove an electron from an atom. Since the outermost electrons become farther from the nucleus as we move downward, less energy is required to remove them. Therefore, the ionization energy decreases down the group. Lower ionization energy means electrons are lost more easily, which explains why reactivity increases from beryllium to radium. Although group 2 elements are reactive, they are less reactive than group 1 metals because they must lose 2 electrons instead of 1. Removing the first electron requires energy, and removing the second electron requires additional energy. Therefore, group 2 metals do not react as violently as alkali metals. For example, calcium reacts with cold water, but magnesium reacts only slowly with cold water and more rapidly with hot water or steam. Beryllium is even less reactive because its small atomic size allows the nucleus to hold its valence electrons very strongly. Group 2 metals are also good conductors of heat and electricity because they contain free-moving electrons within their metallic structure. Compared with alkali metals, they are generally harder, denser, and have higher melting and boiling points. This is because each atom contributes 2 valence electrons to metallic bonding instead of 1, producing stronger metallic bonds. Stronger metallic bonds require more energy to break, making these metals harder and less soft than the alkali metals. These elements are called alkaline earth metals for 2 historical reasons. First, the compounds formed by these metals, especially their oxides and hydroxides, produce alkaline or basic solutions when dissolved in water. Second, many of these compounds were originally found naturally in the Earth's crust as minerals, so early scientists referred to them as earths. Combining these 2 ideas gave rise to the name alkaline earth metals. Group 2 metals readily react with oxygen to form metal oxides. For example, magnesium burns with a brilliant white flame to produce magnesium oxide. They also react with chlorine to form ionic chlorides such as calcium chloride and magnesium chloride. Many of these compounds are important in daily life. Calcium compounds are essential for bones and teeth. Magnesium is an important component of chlorophyll in plants. Barium compounds are used in medical imaging, and strontium compounds produce the bright red color seen in fireworks. The most important concept to remember is that every group 2 element has 2 valence electrons and the general outer electronic configuration ends. These 2 electrons determine the position of the elements in the periodic table, explain why they form M-ions, why they are moderately reactive, why their reactivity increases down the group, and why all members of the group have similar chemical behavior. Once you understand that the chemistry of group 2 is controlled by its 2 valence electrons, it becomes much easier to understand all of the physical properties, chemical reactions, and periodic trends of the alkaline earth metals. The name S-block comes directly from the way electrons are arranged inside an atom. In chemistry, electrons are not placed randomly around the nucleus. Instead, they occupy specific regions of space called orbitals, and these orbitals are grouped into four main types: s, p, d, and f orbitals. Every element in the periodic table is classified into one of these four blocks depending on which orbital receives the last electron during the filling of the electronic configuration. If the last electron enters an s orbital, the element is called an s-block element. This is the simple rule that gives the s block its name. To understand this idea, it is important to know that electrons fill orbitals in a definite order according to the Aufbau principle, which states that electrons always occupy the lowest energy orbitals first before moving to higher energy orbitals. The first orbital to be filled is the 1s orbital, followed by 2s, then 2p, 3s, 3p, and so on. Every orbital has a maximum capacity. The s orbital can hold only 2 electrons, the p orbitals can hold 6 electrons, the d orbitals can hold 10 electrons, and the f orbitals can hold 14 electrons. Since the s orbital holds only 2 electrons, the s block contains only 2 groups, namely group 1 and group 2. The image explains this concept using 2 examples, sodium and magnesium. Let us first examine sodium. Sodium has an atomic number of 11, meaning it contains 11 electrons. Its electronic configuration is 1s, 2s, 2p, 3s. This configuration tells us that the first 2 electrons occupy the 1s orbital, the next 2 occupy the 2s orbital, the next 6 occupy the 2p orbitals, and finally the last electron enters the 3s orbital. The important point is not where the first electrons go, but where the very last electron is placed. Since sodium's last electron enters the 3s orbital, sodium is classified as an s-block element. Now consider magnesium. Magnesium has an atomic number of 12, so it contains 12 electrons. Its electronic configuration is 1s, 2s, 2p, 3s. The first 11 electrons occupy exactly the same orbitals as in sodium, but magnesium has 1 additional electron. This 12th electron also enters the 3s orbital, filling it completely. Therefore, magnesium's last electron also occupies an s orbital. Since its last electron enters the s orbital, magnesium is also classified as an s-block element. Notice that sodium ends with 3s, while magnesium ends with 3s. Although one atom has 1 electron in the 3s orbital and the other has 2 electrons in the same orbital, both are still s-block elements because their last electron enters the s orbital. This is the key idea shown in the center of the image, where arrows from both sodium and magnesium point toward the statement last electron enters the s orbital. The flow diagram at the bottom of the image summarizes the classification process in 4 simple steps. First, determine the electronic configuration of the atom. Second, identify the last electron in that configuration. Third, determine which orbital contains the last electron. Finally, classify the element according to that orbital. If the last electron is found in an s orbital, the element belongs to the s block. If it is found in a p orbital, the element belongs to the p block. If it enters a d orbital, it belongs to the d block, and if it enters an f orbital, it belongs to the f block. The image also compares the s block with the p block. In s-block elements such as sodium and magnesium, the last electron enters an s orbital. However, in p-block elements such as aluminum or chlorine, the last electron enters a p orbital. For example, aluminum has the electronic configuration 1s, 2s, 2p, 3s, 3p. Although aluminum contains electrons in the s orbital, its last electron enters the 3p orbital, so it is classified as a p-block element, not an s-block element. Similarly, chlorine has the configuration 1s, 2s, 2p, 3s, 3p. Its last electron also enters a p orbital, so chlorine belongs to the p block. This shows an important principle of periodic classification. The block of an element is determined only by the orbital that receives the last electron, not by all the orbitals occupied by the atom. Every atom contains electrons in s orbitals because electron filling always begins with the 1s orbital. However, an element is called an s-block element only if its outermost or last electron occupies an s orbital. The reason group 1 and group 2 are the only groups in the s-block is related to the capacity of the s orbital. Since an s orbital can hold a maximum of 2 electrons, only 2 different outer electronic configurations are possible, ns and ns. Elements with the outer configuration ns are placed in group 1, while elements with the outer configuration ns are placed in group 2. Once the s orbital becomes completely filled with 2 electrons, the next electron must enter a p orbital, and the element then belongs to the p block instead of the s block. Another important point is that the value of n, which represents the principal energy level, changes as we move down the periodic table, but the classification rule remains the same. Lithium ends with 2s, sodium ends with 3s, potassium ends with 4s, rubidium ends with 5s, cesium ends with 6s, and francium ends with 7s. Similarly, beryllium ends with 2s, magnesium ends with 3s, calcium ends with 4s, strontium ends with 5s, barium ends with 6s, and radium ends with 7s. Although the principal energy level changes from 2 to 7, the last electron always enters an s orbital, so every one of these elements belongs to the s block. The s block contains some of the most reactive metals in the periodic table because their valence electrons are present in the outermost s orbital. Group 1 elements have 1 valence electron and easily lose it to form M ions. Group 2 elements have 2 valence electrons and lose both to form M ions. Their chemical behavior is therefore directly related to the presence of electrons in the outermost s orbital. The easiest way to identify an s-block element is to write its electronic configuration and look only at the last part. If the configuration ends in s or s, the element belongs to the s block. If it ends in p, d, or f, it belongs to the corresponding block. This simple method allows chemists to classify every element in the periodic table quickly and accurately. In summary, the s block is named after the s orbital, not because these elements contain only s electrons, but because their last or outermost electron enters an s orbital during electron filling. Sodium ends with 3s, magnesium ends with 3s, and both are therefore s block elements. The same rule applies to every other element in groups 1 and 2. Understanding this single principle makes it easy to identify s-block elements, understand their position in the periodic table, and explain why they share similar chemical properties.